Good afternoon. I will go through two examples and then I will introduce to you Taylor's theorem with remainder and Taylor's inequality before you take a quiz. Find the sum of the series. Summation n equals 0 to infinity, -1 to the n power over 2n plus 1 factorial times pi over 6 to the 2n plus 1. In this case, what you have to notice is this is odd degree power, and these numbers are the same. So you should be able to relate that with the Maclaurin series of the sine function. That goes summation -1 to the n power over 2n plus 1 factorial times x to the 2n plus 1. Summation n equals 0 to infinity -1 to the n power over 2n plus 1 factorial times x is just any number. So replace that by pi over 6 to the 2n plus 1. Then this series is indeed sine of pi over 6. 30, 60, 90-degree triangle is something you already know. Pi over 6 is the angle on the top. So that's 1 over 2. Any question? The nature of the problem in the next example is the same. Find the sum of the series. Summation n equals 1 to infinity -1 to the n plus 1 power 2 to the n power over n. In this case, if you replace 2 by x, then that's the natural log function's Maclaurin series expansion. Natural log of 1 plus x is summation n equals 1 to infinity -1 to the n plus 1 times 2 to the n x to the n power over n. So summation n equals 1 to infinity -1 to the n plus 1 times 2 to the n power over n is natural log of 1 plus 2. That means natural log of 3. Before I talk about Taylor's theorem with remainder, let me start with nth Taylor polynomial. Taylor series of the function f at a is f of x equals summation n equals to 0 to infinity. Nth derivative at a over n factorial times x minus a to the n power. When we say the given polynomial is the nth Taylor polynomial, of f at a and remainder, that means we just think about the first n plus one term, case derivative. And Taylor polynomial of the function f at a is denoted by t sub n of x. Thus summation k equals to 0 to n case derivative of f at a over k factorial times x minus a to the k power. R sub n of x is f of x, the given function, minus t sub n of x. That is called remainder. Let's suppose that the function f can be written as nth Taylor polynomial. So this is just polynomial, not infinite, without not infinite terms polynomial, infinite series. And that is written as t sub n of x plus r sub n of x. And limit n goes to infinity, r sub n of x equals to 0, or absolute value of x minus a is less than r. So within the convergent radius of convergence, then f of x can be written as a Taylor series like this on x minus a less than r. F of x is just a function. So R sub n doesn't really have to be the polynomial form, but what it says is limit R sub n goes to 0. This remainder term, or remainder part, goes to 0 as n grows. Then the statement says that this nth Taylor polynomial will converge to the function as a Taylor series. It sounds like a common sense. Taylor's theorem with remainder. Let's suppose that f is n plus 1 times differentiable. And a is in the interval. Then nth Taylor series is k equals 0 to n, phase derivative of f at a over k factorial x minus a to the k power. So this is the nth Taylor polynomial of f at a. So of course, we know that R sub n of x is f of x minus t sub n of x, that is nth remainder. Then Taylor's theorem with remainder says for each x in I, there exists a real number C between A and X such that R sub n of X is n plus 1's derivative as C over n plus 1 factorial times x minus a to the n plus 1. And Taylor's inequality says if there exists m such that n plus 1's derivative at x is less than or equal to m for all x in the interval, then R sub n of x nth remainder is bounded by m over n plus 1 factorial times x minus a to the n plus 1 for x in I. What's happening here is we want to compare the function with the first n plus 1 term in the Taylor series. So just polynomial rather than series. And then we want to think about the maximum bound of the possible error when we eliminate the remaining terms beyond n plus 1th derivative. So we want to think about approximating the function with a polynomial that we know the characteristic a lot better than the complicated function. And then we want to think about when we consider the function approximately similar to certain pattern of the polynomial, how much error can occur? That's the subject we wanna think about. And Taylor inequality and Taylor's theorem with remainder tells us what amount of error we can anticipate. I will return the last week's quiz and you will take a quiz.